Water potential is the potential energy of water per unit volume relative to pure water in reference conditions. Water potential quantifies the tendency of water to move from one area to another due to osmosis, gravity, mechanical pressure, or matrix effects such as capillary action. Water potential has proved especially useful in understanding water movement within plants, animals, and soil. Water potential is typically expressed in potential energy per unit volume and very often is represented by the Greek letter. Water potential integrates a variety of different potential drivers of water movement, which may operate in the same or different directions. Within complex biological systems, it is common for many potential factors to be important. For example, the addition of solutes to water lowers the water's potential, just as the increase in pressure increases its potential. If there is no restriction on flow, water will move from an area of higher water potential to an area that has a lower water potential. One very common example is water that contains a dissolved salt, like seawater or the solution within living cells. These solutions typically have negative water potentials, relative to the pure water reference. If there is no restriction on flow, water molecules will proceed from the locus of pure water to the more negative water potential of the solution. Flow proceeds until the difference in solute potential is balanced by another force. For example, pressure potential. Components of water potential. Many different factors may affect the total water potential, and the sum of these potentials determines the overall water potential and the direction of water flow. Where is the reference correction? Is the solute or osmotic potential? Is the pressure component? Is the gravimetric component? Is the potential due to humidity, and is the potential due to matrix effects? All of these factors are quantified as potential energies per unit volume, and different subsets of these terms may be used for particular applications. Different conditions are also defined as reference depending on the application. For example, in soils, the reference condition is typically defined as pure water at the soil surface. Pressure potential increases as water enters a cell. As water passes through the cell wall and cell membrane, it increases the total amount of water present inside the cell, which exerts an outward pressure that is opposed by the structural rigidity of the cell wall. By creating this pressure, the plant can maintain turgor, which allows the plant to keep its rigidity. Without turgor, plants will lose structure and wilt. The pressure potential in a plant cell is usually positive. In plasmolysed cells, pressure potential is almost zero. Negative pressure potentials occur when water is pulled through an open system such as a plant xylem vessel. Withstanding negative pressure potentials is an important adaptation of xylem. This tension can be measured empirically using the pressure bomb. Osmotic potential. Pure water is usually defined as having an osmotic potential to solute. Potential is given by the Van 't Hoff equation, whereas the concentration in molarity of the solute is the Van 't Hoff factor. The ratio of amount of particles in solution to amount of formula units dissolved is the ideal gas constant, and is the absolute temperature. For example, when a solute is dissolved in water, water molecules are less likely to diffuse away via osmosis than when there is no solute. A solution will have a lower and hence more negative water potential than that of pure water. Furthermore, the more solute molecules present, the more negative the solute potential is. Osmotic potential has important implications for many living organisms. If a living cell is surrounded by a more concentrated solution, the cell will tend to lose water to the more negative water potential. Matrix potential. When water is in contact with solid particles, adhesive intermolecular forces between the water and the solid can be large and important. The forces between the water molecules and the solid particles in combination with attraction among water molecules promote surface tension and the formation of minici within the solid matrix. Forces then required to break these minici. The magnitude of matrix potential depends on the distances between solid particles, the width of the menisci, and the chemical composition of the solid matrix. In many cases, matrix potential can be relatively large in comparison to the other components of water potential discussed above. Matrix potential markedly reduces the energy state of water near particle surfaces. Although water movement due to matrix potential may be slow, it is still extremely important in supplying water to plant roots and in engineering applications. The matrix potential is always negative because the water attracted by the soil matrix has an energy state lower than that of pure water. Matrix potential only occurs in unsaturated soil above the water table. If the matrix potential approaches a value of 0, nearly all soil pores are completely filled with water, i.e., fully saturated and at maximum retentive capacity. The matrix potential can vary considerably among soils. In the case that water drains into less moist soil zones of similar porosity, the matrix potential is generally in the range of -10 to -30 kilopascals. It is worth noting that matrix potentials are very important for plant-water relations. Strong matrix potentials bind water to soil particles within very dry soils. Plants then create even more negative matrix potentials within tiny pores in the cell walls of their leaves to extract water from the soil and allow physiological activity to continue through dry periods. Germinating seeds have a very negative matrix potentials, creating water uptake in even somewhat dry soils and hydrates the dry seed. Empirical examples: soil plant air continuum at a potential of 0 kilopascals. Soil is in a state of saturation. At saturation, all soil pores are filled with water, and water typically drains from large pores by gravity. At a potential of -33 kilopascals, or 1/3 of a bar, soil is at field capacity. Typically, at field capacity, air is in the macropores and water in micropores. Field capacity is viewed as the optimal condition for plant growth and microbial activity. At a potential of -1,500 kilopascals, soil is at its permanent wilting point, meaning that soil water is held by solid particles as a water film that is retained too tightly to be taken up by plants. In contrast, atmospheric water potentials are much more negative. A typical value for dry air is -100 megapascals, though this value depends on the temperature and the humidity. Plant water potentials are intermediate, and this creates a passive flow of water from the soil through the roots to the leaves and then into the atmosphere. Measurement techniques: a tensiometer, electrical resistance gypsum block, neutron probes, or time domain reflectometry can be used to determine soil water potential. Tensiometers are limited to 0 to -85 kilopascals. Electrical resistance blocks is limited to -90 to -1500 kilopascals. Neutron probes is limited to 0 to -1500 kilopascals. And TDR is limited to 0 to -10,000 kilopascals. A scale can be used to estimate water weight if special equipment is not on hand.